talk about some of the work that we have done at Azure for securing our services. And by definition, because we are running a hypercloud, hypercompute cloud, we basically have very large scale of data, and we end up running data analytics and doing data science on that volume of data. So without much ado, I'm going to move forward and make sure that I can go to the next slide. So on agenda for today, I'm going to briefly talk about security at cloud scale, right? So what does it mean to be building security solutions at cloud scale for Azure? Then I talk about geo-anomaly detection algorithm, the algorithm that we have built for detecting login anomalies. And then I talk about graph analytics for detecting multi-stage attacks on Azure, for Azure Cloud. So when you see the scale of a cloud computing system, right? So we know that Amazon Web Services is #1, Azure is #2, there's Google, IBM, and other things. But at Microsoft Cloud scale, we see like 18 billion authentications on a day, in a single day. So that's the number of people who are logging in into the system. There are 500 million active users logging in or using the system in a day. 30 million login anomaly attacks that we detect, and I can talk about how we're detecting this and what we are doing. And 1.5 million compromise attempts that we can detect, and there are 77 million threats that we detect on various devices. So there's a tremendous scale here, and then there's also a lot of interest from attackers to attack this, right? To attack our customers, to attack us. And therefore, it's very important. Yes, you have a question?
So when you say Microsoft account authentication, they're talking about system level accounts or live.com accounts?
That's a combination of both. The Microsoft accounts, which is all of those and also enterprise accounts. Yeah. So what's happening is that because of workloads moving to cloud, the security posture is changing significantly, right? So this is what traditionally used to happen for securing cloud, for securing infrastructure. So you typically have, like a network. You have like a network with a perimeter, and you have some, ingress and egress points. Like typically, you have a firewall. You configure your firewall. You have your routers. And then basically you have everybody else is on the internet, and they're accessing your service through those firewalls and through those routing points. And then you have you've deployed your service internally with Active Directory, and you've got different file servers, application servers, SQL, and this is your traditional model of software development. When you deploy this in your own data center or your traditional model of development. But what happens is that when you move to the cloud, the security posture totally changes. Because what you're now doing is you're building your service, you're building a solution by combining a lot of different cloud services, right? So, for example, you might use Azure Storage to store data as opposed to putting it into a database. Or you might use Azure SQL. You might use VMs to do some processing. You might use platform as a service components. You might use Keyboard to store keys. Now, all of these are really cloud services that are running in the cloud, and they are accessible by various anybody on the internet, basically. So, well, there are a lot of features Azure is working on for locking down these services, but typically out of the box, when you deploy something on the cloud, and this is true for all cloud providers, is that by definition, because this is cloud-based infrastructure, it's very easy. You go to your browser, you just spin up a service, and then you start working on it. You spin up a storage system, and then you start working on it. But guess what? This is now accessible to everybody else. Any attacker can also access the same endpoint and the only thing that's stopping them from actually accessing your data is some security, the password that you have put, or something you have done to secure your system, right? The thing is, the attackers are very much interested in trying to breach your systems, trying to, if you have sensitive data, or if you have data about celebrities or anything else that people are interested in, they would like to attack your systems. And so what happens is that the things that you're defending or you're protecting has now changes in the cloud. Right? So in the past, you would want to protect a server because you don't want to have a malicious actor get access to the server. Now you need to protect the services that you're running in the cloud. Right? You might have a Azure SQL database, and you want to make sure that you're not using admin as a password for that. You have your domain traditionally you have Active Directory domain, and here you have subscriptions in the cloud. You have Azure subscriptions, and you need to make sure your subscriptions are protected and they're secure. Traditionally, you may have a domain admin, so equivalent is you have a subscription admin. On a network in the past, there used to be like lateral movement would happen through pass the hash attacks. Now lateral movement would happen through credential pivoting. And by lateral movement, what I really mean is that somebody, let's say, compromises one part of your system. From that compromised system, they would move to other systems to basically get the maximum coverage, to get the maximum breach that they can do, so that either they want to persist themselves or they want to extract more data, exfiltrate more systems. Right? So essentially, the mindset is very different. How you define a cloud system has to be different, and that basically means that we need to work on this in many different ways. Of course, the first thing that we always do is we talk about prevention. What can we do to reduce the surface area of attack so that the services are secure and the attacker does not even have a chance to access your service as much as possible. And in cases where that's not possible, then you talk about how do you detect if an attacker has got into your system. And I'm going to talk about one such system, which is login system, right? So you all have personal logins, you also have enterprise logins, and the only thing that's preventing somebody else from getting into your account most of the time is your password, the username and password. And many companies also implement like a multi-factor authentication. To give a second factor, like you might have to enter a code on your phone, or you might get an SMS message. So that can be a factor. But once if an attacker gets these things, they're basically into their account. They can read your email. They can do whatever they can do with their account, right? So our goal is, we are trying to do what we can to detect such things and protect against those kinds of attacks. So one of the things that we do is we look at the location from which a request is coming from, right? So typically, when you use your own account, when you use your own service, you have a certain pattern of usage. At work you will log in from a certain place, from at home you log in from a certain place, on your mobile devices you log in a certain ways, and you typically travel to very certain work locations and you do it in certain ways, right? So if we see something, coming in from a location that typically would not be, let's say something happened from North Korea or Nigeria, that's most likely malicious. Right? Yeah, that's most likely not you. Somebody else got your password and they're trying to log in. So the idea with this algorithm is that how can we use information about your basis of location from which you log in from? Yes.
I'm just wondering, can somebody spoof their location? Like, is that easy to do, or that's not?
That's a very good question. What we do is we try to extract the location from the IP address. Generally, spoofing IP address is hard. So there are things you can do. Like for example, you can go on a Tor network, which is like a dark net, and then it's going to route your request to different IP addresses. Now, in a way you can try to hide your true IP address. But we have detection for that also. We can know that you came from a Tor network. So the fact that you did that itself becomes suspicious. The fact that you're trying to hide yourself becomes suspicious, right? So, but yeah, there are things you could might try to do, but So the simple thing that we say is that, hey, if you have seen a certain pattern of access from you, then the attacker also has to know that pattern and has to try to emulate it. Right? If they can't do that, then we will find that as an anomaly. Even if they spoof it, if let's say they're coming, a North Korean attacker might say, hey, I'm coming from someone in the US, right? They can use a proxy and they can try to log in from a proxy. But then if they're logging from a proxy, not typically when you log in from, then it's still suspicious, right? So basically talk about how you could do like a geo anomaly detection, right? An intuitive algorithm might just say that and look at the locations from which a user is coming from, store the locations for some time, build a history of all the places you are coming from, and then if anytime you're coming from a location that is not in your past, let's say 10 locations, then that seems suspicious, right? But the thing is that what we find is that doing something like that has a lot of noise because you can come in from a company proxy, right? You might be coming through VPNs within your company, which is perfectly fine. You would use cell phone networks, and cell phones will route your requests to different towers in different locations. So the IP addresses change a lot. You might be on vacation, traveling. That also, you might want to log in from there. So what we did was when we do a simple rule-based stuff, we get a lot of logins are found as suspicious, right? 28%, which is like a huge number, and there's really it's impractical to kind of work with that kind of a number. So, but when we use machine learning approaches, we were able to reduce that call rate to a very small percentage, of 0.001%, and with the precision of compromise rate that we can detect at 50% or higher, right? So in security space, 50% is a pretty good number to be able to know whether a login is happening from a suspicious or malicious pattern. So I'm going to talk about what algorithm we use and how we use there. This is just a philosophical slide about the fact that we want to minimize the false positive rates and maximize the true positive rates. So I'm going to explain briefly what algorithm we use, and then we'll talk about how we made it work and operational. So what we do is we take different sets of users, right? Different users in our system, and we look at their past login behavior. We look at, let's say, 45 days of login behavior, and then based on the frequency of their login. So, for example, user 1 here logs in from Comcast Bellevue more frequently, and logs in from Microsoft Redmond. Now, here Comcast and Bellevue is a combined thing, is a carrier and location, because carrier is a very important indicator of the location you're coming from. Because let's say if you have Comcast at home, then you would come to use Comcast. If you are at Microsoft is its own carrier or a network. Similarly, you might have Verizon on your cell phone, so you'll come from Verizon. But if you suddenly come from some other network, that is suspicious. And a lot of the times when attackers try to fake their location or spoof their locations, they come through some of these proxies or networks which are not very standard. So that helps us to catch them there. So once you have this location from which the users are coming in from, what we can do is you can compute. This is like a bipartite graph of user and the location where they log in from. Based on that, you can compute some similarity between the users, right? So you can compute like how similar users are. This is a very common collaborative filtering approach. Like when you go to Amazon, you buy something, it says, hey, based on your buying behavior, you can see other people who have bought similar things. So then you can count similarity between people who what they're buying. Similarly, from what we do is logins, we see where you're logging from, and based on that we kind of find similarity between the users, and we score that. So like this is a graph. This is basically a graph where you're showing the user and the other user the similarity to that. So to themselves, they're one because they're exactly the same themselves, and user 1 with user 2 is like 0.8 similarity, 0.7 with user 3, etc. Right? So there's nothing good for user 4 because we think there's no similarity, they're different users. So once we have this information, then what we can do is we take for a given user, we try to find out all the different locations the user is likely to log in from. Right? So the reason we do this user-to-user similarity is because let's say we have, in the 45-day period, you might not have gone to a company proxy. Or you might not have traveled to a location where a lot of people from your company travel to rather. Because, let's say you have a satellite office in San Francisco, but all of your colleagues go there, but you have not gone there, right? But we want to know that that's a location you'll most likely log in from, because, you might travel there sometime. So the idea is that based on similarity, we can find out all the locations that you're likely to log in from, right? So that will give us a kind of idea of the places where you're logging in from. And then if you're logging in from a location that is not a likely location, then that definitely raises suspicion, right? That kind of raises suspicion that, okay, how come you're logging in from a place which you typically are not expected to be there? So, so once we have that thing, this random walk example basically shows how we compute that reachability data. Right? So it basically shows, for a given user, we are basically doing a Monte Carlo simulation. Right? We are taking a user based on similarity. We are trying to, based on that probability, moving to those users. And then we do that a few times. And then after we have done that, we basically choose the location from which that user is has logged in from, and make all of those locations as possible locations that user can log in from with certain probabilities. Right. So now this is the other aspect is about travel, right? So you might be genuinely traveling, and when you're traveling on vacations, you go to a new location. You won't be going to the same location you could, but generally you go to new locations, right? So, so when we consider that, we look at the speed of travel, right? So, if you log in, let's say from Bellevue, like an hour back, and suddenly after 2 hours you log in from Russia, so like you couldn't be traveling so fast, right? So that's not how fast you travel. So therefore, we say speed of travel, right? So, but suddenly, let's suppose there's no activity seen from your account for a day. And then after that, you see login from Russia, then most likely you might be traveling, so that seems less. So now we have the reachability data, which was based on the location that you're likely to reach, and then the speed of travel is how much time you are from the previous login to the current login. How much is the distance between the locations, and how much is the time it takes to travel between those locations. So using this information, we basically put together a Markov chain model, which basically comes up with an estimate of how suspicious that login is. So it's an estimate that's combining the speed of travel and the reachability, and combining that information and say if let's say your speed of travel was too fast, like you've traveled to a location within like an hour, which you can't, and your reachability was low, then definitely that has to be suspicious, right? And so we kind of track that. So that's kind of what we use to reduce our the false positive rates and to get good precision on the compromised potential compromised user when the attacker is logging into the system. So that's the algorithm. And but in terms of cloud scale, so this algorithm runs on Active Directory logins, not the currently does not run on the Outlook.com or Live.com. It runs on Active Directory. So these are enterprise logins that typically companies who are using Microsoft services, Office 365, and other Microsoft resources. They basically all are authenticated through Azure Active Directory. And so the scale here is still huge, right? We're processing 10 billion logins here, tens of petabytes of data, 300 million active users in the Active Directory space. So the question is, we have a good algorithm and we have a huge scale. So we need to be able to run that algorithm in production at a way that you can process that information really fast. So this is kind of the architectural diagram of what we're running in production for the geo-login anomaly detection algorithm. So what we do is we do a bunch of the reachability calculations in an offline training pipeline. So it's like a MapReduce. Cosmos is similar to like a MapReduce system, it's Microsoft proprietary. And we train those models, which for every location it's able to, like given the user and their past history, it can look at a current given location and say what's the likelihood that this person will log in from that location. Right? So that we do offline analysis, and then in the near real time, which is basically as the users are logging in, we get the stream of events. So this is like an event hub. An event hub is very similar to a Kafka system, which is basically a queue of events that's coming in. So every time a login event comes in, it comes into the event hub, and then we have a cloud service, which is reading data from that event hub, and each login record is extracted, and then the user's history is first bit, right? So if the user is coming for the first time, we don't have any history of that. We basically build a history of the user over a certain time. And once to build the history, we basically store that login information into a store, into a persistent store, and basically store the past logins for that user in that store. And from that, we generate a bunch of features. That features are used with the offline trained model to score a login, right? So it says what's the reachability likelihood of this, and we also have the past location, so we can do the Markov chain evaluation, see how much is the speed of travel between the previous login and the current login, and then all of that information is used to come up with a score for the anomaly score. And that anomalous events that are anomalous are basically sent out to an event hub. These are all the logins that are anomalous. So once you have the anomalous events out, then based on that, we can update the user's risk score. We can require them to change password and do different things. Yeah.
I have a question about your model updater.
Yes.
So you're retraining the model like I don't know every night or whatever.
Yes.
And then you're updating the model, but every time a new model is published, wouldn't that impact your thresholds? Like what determines a suspicious likelihood, or everything is just like?
Yes. No, that's a good point. I think every time we deploy a model, right, that would change how a particular login is rated, how suspicious it is rated, right? What we do is we make sure that from a day-to-day change, it does not cause a massive change. Right? So the changes are incremental. Right? So the changes or the differences are incremental. Primarily because we are looking at data over like 300 million users. We are looking at the data over like 30-day period or 60-day period actually. So basically, since every time we train, we do a weekly training process. So the data that we have is basically about a new week of addition and about a new week of data removed. So that the change in the model is not much. And also because there are so many users and there's not much of a difference that we see every time.
But then periodically, would you reevaluate the level that what you determine as suspicious or not?
Yeah, so the levels are, we have not changed the levels at which we evaluate suspicious or not. But what we do is we periodically have evaluation where we grade everything we found suspicious and anomalous. And we see what is our true positive rate and what's the false positive rate. So far we haven't, I think most of the time when we find that, actually we are missing something or, we are flagging something many times, it is mostly related to some aspect of the feature of the system, right? So let's say, there are certain networks which the company has where people log in from most of the time. So the companies can tell us that these are all IP addresses that belong to us. So we can consider them as safe, right? So then we can whitelist them and then we don't run. So we do things like those also to reduce the false positive, but we keep monitoring that way. And if something changes, we look at what it is. Generally, threshold so far has not been one of the things we have to change. Okay. So yeah. So that kind of really, yes.
So you do allow the user to log in. If you think it's malicious login, you only go back to the data. Let them log in first.
That's a good point. This algorithm runs in near real time, right? So if it was running in real time, we could block the user from getting on. But this one is we basically let the login go through, and after that we update within a few minutes. We update the user's risk and we update the users. And then you can set conditional access policies where you can say, hey, if I see a user has a certain risk, you want the user to change password. Currently, we don't have a way to revoke a session in Active Directory, but we are working on that feature where we can say that, hey, if you think this user was suspicious, you can even revoke the session, and say, you've got to log in again. And when they log in again.
So if you think you have a bad session, you can't stop it?
We can stop it if it happens in real time.
Right. But once you, if you know you have, or you suspect that you have an active session that's gone bad,
right?
You can't cancel it right now.
Right now, you can cancel it within a certain scope. Like, for example, let's say you log into Office, right? So Office will have its own cookie, and it will cookie you, and then it won't check again, right? So there are lots of systems in place.
Oh, you can't push that because you can't touch the. Okay,
right. So, but we are working with all the teams to make sure that we have the ability to basically broadcast to all the systems that are using that authentication token to say that, hey, this is now invalid. This person can no longer use it. Yeah.
Question about remote. Have you also tried using time uploading?
Sorry?
Have you also, along with the place uploading, have you tried using time? For example,
time, yes, place and time.
Like on a week.
Yes, we did experiment a lot with the time of the login, right? Yes, and we found that you look at time as in time from the previous login, but you could also look at, let's say, you're logging in the middle of the night, or we tried those models, and that was very noisy. We found that to be very noisy for various reasons. One is because people work at odd hours all the time, especially in the tech industry. I guess. Sometimes you're working in late, sometimes you're working early, or sometimes you're not at office. So that hasn't helped us much. Yeah. There was another question. Yeah.
And how do you go about, let's say you have a calculated false positives. How do you know which one was actually a malicious document?
So we have a group of security investigators who basically look at this data. So what they do is they look at each of these logins with the context of the past logins and other data about the user, and they actively evaluate it. So they're manually going through these things and they grade them. And based on what they're seeing, they say, this definitely looks suspicious. Or they might also say, I don't know, I can't say for sure. In which case, we sort of spot it about notes. Yes.
So we don't.
Third.
Yeah. So we don't confirm it with the user.
So yeah, no, that's a good point. We have we do confirm with users with companies we have close partnerships with. So we have some of the companies who are close partners. We share the data and they tell us that this was good or this was not good. But that is only those companies that are working with us closely on. Because we in the enterprise space we are not able to currently go ask the user directly. But we are also working on a feature where users can look at their past logins and say that hey, that was not me, or they can give the feedback. One of the challenges we see in that space is many times users don't give us accurate information. For example, you might look if you have a Hotmail or Outlook account, you just go see your past login. You'll be surprised that you're logging in at 3 a.m. in the morning because your phone is ringing on your behalf. And you go, that's not me. I was not awake. I was sleeping. But it's because so things like that happen. Yeah, sorry.
If I'm on a team and we have a shared account and I didn't know that I was supposed to tell you, how badly will that mess you up if I'm logging in Seattle and then 30 minutes later a teammate is logging in Shanghai, but they're both valid logins on a shared account?
Yeah, I think we really don't encourage shared accounts. We really suggest that it's not a good security practice. Mm-hmm. If you're going to flag it, and we think you should actually not use shared accounts. Have separate accounts.
Oh, I agree. But users are stupid.
If you're doing it from day one, it might show up like a VPN. It'll just be normal for you.
Yes, that could happen for that.
Right.
Yeah. Yes.
Just to understand the scale, how many people do you flag suspicious per day?
So on a given day, we are flagging around 2,000 and thousands from all the.
And some have more than 1,000.
We don't investigate all of them. So we take a sample of them to investigate. Right. So typically in a week we investigate 500,000. Yeah.
How do you decide which?
You just take a random sample.
Okay.
Are you also actually
It's a good point, actually. A very good point. And I think the rest of the slide presentation, I will talk a little bit about that. The activity after the log, other things.
You mentioned this wasn't in use for like Outlook or whatever.
This particular algorithm is not in use.
Is there a reason that you aren't using it across the board?
So in the case of Outlook, we have an algorithm which is called a familiar allocation, which is more of a rule-based thing, and it runs in real time.
Okay.
In AD also, we have a real time, the same algorithm runs here. So one of the good things about Outlook is that we get much better signal about the login behavior, because we almost a very high percentage of users, close to 100% of users have the MFA configured. But that means you have to have some kind of proof of your email address, of your phone number, or something that we can download an SMS code to. So on Outlook and Hotmail, we are able to, even for small suspicions, we are able to force MFA and get that kind of validation. But in enterprise space, not everybody sets up their account for MFA. Because the administrator has to do that. It's not an end user choice. The company has to decide that they're going to set up some security for you. And so it's kind of a little different. And this helps us a lot in patching that.
You said near 100% for Outlook of
Yes. So we
your user base?
We require, when you sign up for an Outlook or an Hotmail account, you must have a phone, you must provide a phone number. So we make sure, and we also have done a lot of work to make sure that the existing users, they all provide some.
Interesting. Okay, cool.
Yeah.
How secure is your fingerprint signing in? Will that solve some of these problems?
I think there are lots of technologies, for biometrics, and so I think Windows Surface, and also has Windows Hello, where you can does a facial recognition. Yeah. So I believe they're very secure. I'm not testing them myself. They will definitely, I think so. In fact, having some kind of a registered device in which you have registered biometrics makes it more safe. We recommend that. In fact, require it for all Microsoft employees to use that.
If your device gets compromised and somebody's in the middle of the transaction, though, it doesn't fix any of it.
Yes, if your device gets compromised, then
Coming from a bank, so we deal with compromised users a lot.
If somebody steals your phone and if you're already logged in, then you're...
Well, so it's malware on it, and so then you're still using it, but they're watching everything that happens while your session's going on. They're seeing your multi-factor tokens, they're seeing whatever you submit, your fingerprint hash, etc. But it still will sometimes route through other locations and shows up as anomalies similarly.
yeah. Okay, so thanks for the question. So I'll move on. So once we did this, I was talking about the review, right? Signal quality review, where are there questions online also?
No, that's fine. I just checking.
Okay, all right, cool. Sounds good. So we do this manual investigation where investigators can say, hey, it's a likely compromise, it's an unlikely compromise, or you can say require more investigation, and we get that label data, which helps us to see the quality of our detection that we are doing here. And we also get feedback from customers, right? I blacked out the customer name, but you could see logins happened from Atlanta, New York, and then suddenly Lagos is in Nigeria. And then you see a whole bunch of these logins from Lagos, and the customer says, dude, this is not us, there's something wrong, and you need to patch this, you didn't patch it. So we have some cases like this where we miss, but we collect all the information. And then we use that information to create a supervised model, right? So so far what I was describing was an unsupervised approach. We basically doing collaborative filtering and finding out what location they're logging from. But then in that case, one of the challenges is that we are going to miss a lot of, for example, a login from, let's say, Europe is not as suspicious as a login from Nigeria. It's given everything else the same, right? Or for North Korea, it would be much more suspicious. So what we did was we captured all these features. We got training data about what is true compromise, what's not true compromise, and then we trained a supervised model on top of the unsupervised model. It uses reachability as one of the features as an input. It also uses other features like, for example, the location, the carrier, how suspicious the carrier is, and all that information. And so that helps us improve the precision of our algorithm. That helps us improve and catch them better. So again, this is the training phase, and that's the evaluation phase where we are running the supervised model on top of it's a cascaded thing where you have unsupervised first and then supervised after that. So yeah. That was kind of one of the algorithms I want to talk about, and then I'll move on to talk about the graph analysis for cross-service detection. And this is the idea was, like the gentleman was saying there. If you see what is the user doing after the login, if let's say the login itself was not that suspicious, but then the activities after that seem to be more suspicious, and we can combine all that together, build a graph of the behaviors, and then see that, and then have higher confidence that the user is actually suspicious. So typically, like we are saying that individual detections can catch so much, but attackers will compromise one service, go to the next service, and go to the next service. And that's like a multi-stage attacks that we see. And so if you build these cross-service detections that can identify the stage in the kill chain. So we can say, hey, there was a breach by compromising the password, and then after that they actually sent they installed, let's say, some malware on a machine, or let's say they added added that user to some subscription that they're not supposed to, or that's sensitive. So all of those actions in the kill chain of when I say kill chain, it's a very security specific term. I don't know how many people relate to that. It's basically maybe I'll briefly refer to that. It's a military term, which basically says that when you want to go to a target, like you want to get a target, you basically go through different steps. Like you do reconnaissance to find information. You do some weaponization to figure out how you are going to what weapons are you going to use, and you're going to do delivery to get your weapon there, and you're going to at different stages and different. So the kill chain is basically saying that you want to get to some objective, right? To get that objective, you go through the different stages. Every attacker, to get to the objective, will have to go through those stages. And for every stage, if you can have some kind of a detection or some kind of a alert that it is suspicious and that's suspicious, then you can say that you can combine the whole thing and say, oh, look at this seems to be forming a kill chain where the attacker is going through these steps, and now the attacker might do something like that, right? So that's typically what at a very high level what it means in terms of kill chains. And so what we do is that we are taking data from different services in Azure, like Azure Resource Manager has different activities to perform on Azure. You can have administrative behavior, so you can create users, or you can add a user to a subscription administrator group. You can we have identity protection detections are like Azure login and Omni I was talking about. We can look at mails that you're getting. If you're being targeted by phishing mails, there's a chance that you might click to them. We also have other services. So we're putting all of this information into a graph and saying that, okay, now we have this information about all the things that the users have been doing here, and how do we, given these graphs, we can identify what is suspicious. But the challenge is that with graphs, it becomes again big very fast. You really quickly start having so many activities you can do, and it becomes really huge really fast. So what we do is then we make an inventory of all known attack patterns, right, that we know. So we have a red team within Microsoft who actually tell us all the things that can be done by an attacker. They can do this, they can do that. And because red teams, they do that all the time, and they have a lot of experience doing penetration testing. We also get information about known attacks in the wild, what's going on, like there's the WannaCry, we see what the pattern that they go through, and there's a whole bunch of these attacks. And then, so based on that, we have this database of all kinds of attacks that we are familiar with. So we we constrain the graph to those attack patterns by applying the kill chain constraints. And then once we have those subgraphs that match those constraints, then we start scoring them and seeing which one of them are actually suspicious. Some of them might be benign because the normal user also might be doing them. So then we score them for suspiciousness, and then that helps us. We use both supervised and unsupervised algorithms here also to detect this. So kill chain connectivity. This is the idea where kill chain phase, like these are different phases of the kill chain. Reconnaissance is when somebody is trying to get information about you so that they can attack you. Delivery is when they actually have some information, some weapon that they can deliver to you. Installation is that weapon has been installed, like if something has been, some malware has been installed, or some backdoor has been opened, or some sub has been opened, stuff like that. Privilege escalation is you can basically get onto a machine as a low privilege user and then try to become an administrator, or you might get an account of just an ordinary user and then somehow make that user an administrator on. So those are all the different stages of the kill chain, right? So you might do exfiltration if you're trying to extract data, and you're doing other actions, and then you might be trying to conciliate, but you might be trying to delete your logs, or you might be trying to delete, things you did. So those are the different stages of kill chain, and we map the different detections that we have to the kill chain, and then we use that to model the stages that the users have gone through. So again, here we use like a Monte Carlo simulation where we look at different kill chains that you can go through. So suppose you're doing something, a reconnaissance activity. If it happens after the installation activity, then that's most likely not a part of the kill chain. So we can remove that. We can remove that as a potential thing. So we do these things, and then based on that, we come up with connectivity score for the graph. And then based on these connectivity scores, we look at we use unsupervised approaches to say how do we score them, and what approaches we take. So we look at the nearest neighbor, we look at similarity between graphs, and based on that, we are able to then find out which ones of these are suspicious and which ones are not. So we so far have got good results, and this is something we are actively actually deploying and working on. And supervised approaches, we use known labels of multistage attacks from all the information that we have, and then we featureize this. We use random polarized.
You said there was one false positive.
Yes.
What happened?
Basically, I think false positives. One false positive is pretty low. I think in that case,
Right.
What happened was that particular user was behaving very similar to what the red team had done.
Yeah.
So they were using the same IP address, and but one of the things is that because the red team is within the company, they also use a similar set of networks. Mm-hmm. So that's kind of the thing that we are doing for being able to catch these attacks that we talked about, and running this on scale. So that's basically it. And in terms of summary, detecting geo-anomaly requires fairly complex algorithms, and attacks in the clouds is not the same as on-prem system. Therefore, graphs are good vehicles for detecting those attacks. I don't know who I'm doing fine, but any other questions? I know you've been asking questions, so that's great, but please could ask me.
I have a quick question. The graph modeling part looks pretty interesting.
Yes.
And I can assume it's very difficult getting those logs in order to generate those logs, right?
I'm sorry, did you say difficult to get the logs?
Right. So are you using some default logs?
Yeah, so we get logs from our services, right? So, like for example, a lot of the security-related things have security logs. If you try to do the login, the knowledge